Hello everybody, my name is Jalu Madiar and I am the scientific coordinator of the project called Artificial Intelligence and Combined Survey Techniques for Stone Quarries Optimization, funded by Aramin 3, Raw Materials for the Sustainable Development and the Circular Economy. Before I dive into the presentation of this project, I would like to mention the partners in this consortium. By Bilişim for Turkey, University of Petrosani from Romania, Faculty of Information Studies in Novo Mesto from Slovenia, University of Bologna from Italy, Geological Institute of Romania. The idea of our project started by knowing that stone blocks such as marble, granite, and sandstone are natural materials with excellent properties and are in high demand in a variety of industries. However, their exploitation in quarries is conditioned by two unfavorable factors. First, these ores have naturally occurring fractures and discontinuities, such as faults, joints, and fissures, which preclude the excavation of larger blocks with bigger commercial value. Second, stone quarrying is a very intensive waste producing process, since not all excavated material is of commercial use. With booming markets, risks to the environment are only bound to become more serious. You can see in these pictures some of the quarries which were investigated by our project. This project partners come together to create an eco-efficient and sustainable stone exploitation by using non-invasive surveys, optimizing production, and reducing waste, energy, and water usage. The key objectives of the project are identification of more suitable geophysical and remote sensing methods for rock mass characterizations in terms of fractures and discontinuities affecting the block's production. Derivation of scalable algorithms for optimal extraction of blocks in stone quarries. Maximize the size of the extracted stone blocks and minimize the environmental impact. And development of a stone quarries optimization software as a system, SQO SAS. The main expected outcomes by the end of the project are the following: a framework for quarry optimization and environmental sustainability based on artificial intelligence algorithms. The framework will manage quarry data, topography, environmental constraints, geophysical measurements, GPR, televiewer, manual scanline, LiDAR data. You see here the measurements of the televiewer, GPR, resistivity, and scanline data, and then LiDAR points. The developed algorithms will be included in the framework in order to supply the final user with information about the best quarry design scenarios, cut directions, block dimensions, in terms of economic value and environmental impacts. You see here some of the algorithms which were implemented or still are in progress, developed by our team. Emphasize the importance of environmental performance certification and labeling, such as eco-label standards and life cycle assessments. In this table, you see the new eco-label system developed by the European Union for quarries, and then some parameters which characterize the eco-label, which is the quality of air, noise, and waste, for example, recovery ratio of the blocks versus the generated dust. Correlating the developed technique for stone quarry with the economic evaluation by calculating and comparing several indicators such as recovery ratio, selling prices, and total earnings, including also the production cost before and after Ai Costsqo solutions. In these graphs, RMV stands for relative money value, and you see the mineral deposits with the fractures modeled in several blocks, and then the total RMV versus the block volume, recovery ratio versus block volume, and the total cost versus block value. And now I would like to show you how we have implemented the software solution via an API through Amazon Web Services EC2 platform. This is the website interface as it is already implemented, and we set up several dummy projects at this stage because the platform is under construction, and we have several tabs: visualizations panel, data, block size distribution, decision support systems. We start by defining the site boundaries, either using a map or coordinates, and then we can add discontinuities from various methods. You see, we visualize, we can see the data. For example, for nothing from the televiewer, nothing from seismic yet, resistivity, magnetometric, but this will be populated sooner. And then we can see the representative prism. This is only one rectangle, and for example, discontinuities inserted from the scanline measure. This is deterministic approach of the problem. We have envisaged to develop both deterministic and stochastic analysis of the fracture system. In this case, data is represented deterministic, and we can visualize this data. And we have got from the intersection of these discontinuities various polyhedrons which established various blocks of different sizes and shapes. And this is the extended 3D version of the representative prism. And we also implemented some routines for discrete fracture network. We can see the discontinuities as deterministic, and if we calculate the discrete fracture network, where the joints, the fissures, are represented in this case by discs, circles, and we can see them. So now we will have to calibrate the discontinuities obtained from in situ measurements, which is on the left side, with the discrete fracture network, which is generated through our algorithms implemented into the software. And we have various distributions for deep direction, and we also have some other sites. This is the team of developers taking care of the data and the various testing projects. I would like to thank you very much for your attention, and if you would like to find out more details about the project or send us a message, please feel free to use the web link below. Goodbye.